Now here's the first example. Verify this is true. So I have fxy equal x squared y squared, and my x is 1, 1, v is 3, 4. Is it true? So doing this partial derivative of this thing, so it will be what? So it will be partial this on x squared plus y squared and partial this on x squared plus y squared, right? Partial derivative don't care about constant, so this one gone, and partial derivative don't care about constant, this one gone. dx squared dx is 2x, 2x, dy squared dy is 2y, 2y, done. And then what? We have x as 1, 1, so 2x, 2y, so 2, 2. Now we have this part. We want this part. So this thing is 2, 2. This v is 3, 4. So it's 2, 2 inner product 3, 4, which is 14. Okay, done. Then what about this part? 1, 1. V is 3, 4. So 1, 1 plus t 3, 4. Again, this is t, not h. I make a mistake. Then I need to write this down, right? My function is x squared plus y squared. So it will be this. So it's x squared. So 1 plus 3t squared. And then y squared. 1 plus 4t squared. Again, this is t, not x. And then this is what? X squared plus y squared. So x squared plus y squared. This thing calculate. Okay, skip the detail. You get this 14. Okay, 4t equal 14. Of course. What's the gradient of the inner product? The formula is this. How do you prove it? Well, I told you, we have partial derivative, directional derivative, Cartol derivative, or Frechet derivative, which these things are the same thing, but just different expression. So we can now starting to use this whole thing to find gradient. So we will use the partial derivative. Why? Because this cx, because it is just what? c1x1 plus c2x2 plus. So if I do partial derivative, each time I only need to just look at one thing. So this is the only case you should use this elementarized. You should only use the elementarized when everything is separable. This is separable. This is the partial derivative on all xi and correct all of them. Okay. And then now this part I copy everything. So this part is here. Now I replace the f. What's the f? F is inner product. I now write down the inner product as summation. Now because partial derivative xj on xi 0, so I get this, and what is it? This is just vector c, so that's why. So how do I find the gradient of this? So if I have qxx, I want to find this, then if I do this, what I have? This part is what? All the row dot product with x, and then this is what? All the x, right? Then very quickly, you now have a lot of ij you need to worry about. This, can you keep going on? Of course you can, but then you need to be very careful. So this is how you do it using the directional derivative. What I'm going to do, this part, f plus tv. What's f? F is this. So now I just write this down. What happened? All the x here I have blue thing. Now I replace with a longer blue thing. Then what about the second part? The second part is the green thing. Well, green thing now change. So it's the green thing. Okay. So therefore, the first line done. The remaining steps have nothing to do with calculus. It's just linear algebra. From here to here. So this is what? A, B, C, D. Then you have A, C, A, D, B, C, B, D, right? Then you just write them down. In this case, AC is QXX, AD is QX TV, BC is QTV X, and BD is QTV TV. And the first QXX and this minus Q each other. So that's why it's gone. So this is the BCD thing. I have, this is T anyway. Then what? Now, here's a funny thing. This one have a T, this one have a T, cancel out. This one have a T, this one have a T, cancel out. This one have two T, doesn't matter. I cancel one of them and I keep the other one. Then when I take limit, this one goes away. Okay. Then I have these two parts. This one goes away. Okay. Now I have this part. Okay. And then what's next? Well, this part, what I'm doing is, okay, mxy is same as xm transpose y. I'm just doing simple thing. Okay. I write it detailed so that you understand. So I put the q to the other side. Why? Because I want to, this is the argument, because I want to have v in one side. You see, look at here, v only appear alone, nothing next to it. Here, v has something next to it. I want the thing gone. So I move to the other side. And then I flip this expression. Now I have v alone, and linear algebra, this is linear, so I can combine them. And because dvfx, directional derivative equal to gradient inner product v, now I get directional derivative as something inner product with v, then this something is the gradient. So gradient of quadratic term, by using the directional derivative, is q plus q transpose divided by 2x. Here, there's no half. So that's why when I have a half, there's a half. Then you may ask why I do this, because this is also called a symmetric factor of q. That means you have a matrix, q, not necessarily symmetry. You want to make it symmetry, you just do this, the last bullet point I said. You can also derive the same result using the partial derivative. Don't. Fx is ax minus b, this is this way. Find this using the previous result. So I have two ways. I will demonstrate to you all the way. Let's do the first way. The first way is I expand this, because this 2 norm is just ax minus b, ax 2 norm, right? So now I expand it, I skip the detail. So I have this d equal sign means I do linear algebra and expand everything. I have this. And then now what? I know this box and I know this box, then I just use the box. So this part is q, this is my q, right? And this is what? This is my c. So this part by the box, this part I have the C. C is A transpose B. This part is the Q. What's the output? Q output is Q plus Q transpose divided by 2. But this time the Q is Q. Q is Q transpose because this is symmetric. So that's why I have E self. So therefore, norm AX minus B gradient is this thing. So this is what? This is assume you know this box and you know this box. What if you don't know the box? Let's do it using directional derivative. This is the same plane. So that means you should get something similar, right? Let's see. So suppose I have this. Find this and assume you don't know the two box. Then I do the same thing. What's the directional derivative? Again, let's go back. I just need to get something that looks like this. So what's my fx is ax minus b. So now I have my x plus tv. I just replace this everything by the x plus tv. Then this thing becomes x plus tv. Then I have this thing. Okay. Once I have this thing, okay, now I move the b to here. I move the tv here, so I get this thing. Okay. And then what? Put a bracket here. Expand linear algebra again. So I do the linear algebra. I get this again. Okay. Again, this part is detailed. So you have this whole thing. Then what? Then this ax minus b is what? This is my f. So this ax minus b is my f. I just rename everything. And now this part, you will remember I want something v alone. Now I have an a here. I always want to go to the other side. So I put the a to here by transpose. So now there's an a transpose here. The a is here. What about t? Well, t is just number. I can put it here or I put it here, doesn't matter. So t doesn't matter. But a is not. So I have this. And then what? And then I have some error. This is t, that's square. So this is t square. Again, t is h. Okay, I make some latex mistake, but you got the idea. So now I have this thing. And what we want is this directional derivative. Again, this is t. Okay? Then what? I want this thing, which is what? What I'm doing here, right? This red thing is this whole thing. This red thing minus fx is this red thing, remove this part. Box is this box. Divide the h, that means t, this one is gone. This one I have one power, gone. Take limit, this whole thing is gone. I get this thing, right? This whole thing, subtract, is this part, which is this part. I have a t, which is h, okay? And then take limit, this part is gone, so I remain is this inner product. This inner product is exactly v is alone something here. Okay, then this something here is the gradient, which is correct. This a multiplied inside is what I want. So this is how you do with definition. Then now, here's a corollary. We now know this, right? So what if b is 0? Then we put b is 0. What if a is identity? We put a is identity. Then we have this. So that means what? That means here's a funny thing. A vector actually is coming from somewhere. A vector is the 2 norm square half. You know, when we learn dx in high school or year 1, we also learn this, right? So now it's the same thing. You know this is inverse, and then this is inverse, something like that, right? Then this is an example. So that means integrate x dx, this is vector, give you back this. Now let's go to more complicated one. The domain is still x, but now the range is Rm. What's Rm? So now this is what? This is what? Input is a vector. Output is also a vector. And here is some notational details. I always use bold f to mean output is also a vector. This thin f, okay, is output is scalar. This is vector. Or I use this, okay? These are vector output. So this thing means what? Rn to Rm function. So now everything changed a little bit. So first of all, but I said everything carries over to infinite dimension. So even this is finite dimension, it doesn't work, it still works. So we still have this, okay? So it's the same thing. But now I change this f to bold color. But now here's a funny thing. This is now inner product. Why? Because now this thing is a what? It's a vector. I call it f1, f2, blah, 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 blah. So when I do this, I'm doing this. But this is a vector, right? So now this is a vector, this is a vector, this is a vector, this is a vector, this is a vector. This is now called a Jacobian. So this is a matrix. So this is a matrix product with a vector. So actually this is what? This is matrix vector product. Matrix vector product give you a what? Give you a vector, which is correct. Which is correct because this guy, the domain is a vector. No, the range is a vector. Okay. So now we talk about with Jacobian. Okay. Okay. With Jacobian. If I have a f, big F, the reason why I write big F is just to specify this is the whole thing and small f is an individual thing. Okay. Then, because now my output is Rm, so I can write m of them, f1, f2, f3, f4, fm. Input is Rn, so therefore this x are vector, n-dimensional vector. And then what is the gradient? The gradient, this is still called gradient, but they call it also the name called Jacobian, which is basically all the ij. And you have this thing, okay? Then similarly, if you have a function, okay, r, let's say r to r mnp, you can define in a similar way. Then of course you have a hypermatrix or tensor, okay? But doesn't matter, okay? Then in this case, what is a particular thing here? It will be ijk, okay? but the same. You know up to level 2 is enough. So this is called Jacobian. It's just name, okay? And this is also called total derivative. Why? Because this is all the okay, partial derivative means you only know one of them, but now you know everybody. Of course, it's total. That's the name, okay? So yeah, it's a total, yeah. And then J exists means what? J exists means all of them exist. So this is a very strong condition, okay? And then we also can do the same thing for the Frechet differentiability. It's basically this, right? This is the Frechet thing, right? Now I write everything in bold because this is a vector output, this is a vector output, this is a vector output, okay? So this is a vector, this is a vector, this is a matrix, but matrix times a vector is still a vector, so you can vector, 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 and then, yeah, no. Okay, so this is the example. Okay, let's do an example. So again, I have this, and then you can do the same thing for following. Okay, detail. So this is the idea, okay? Okay, these are simple example. Nobody care, we don't care, okay? What we care is this, okay? So let's go to here. So now, want to do this. So I have this again. So Rn to Rn, and what? My function is fx is x. Find the gradient or find the Jacobian. So what is this? This is directional derivative, no change. Again, this is t, no h, okay? Then what? This f thing is x. So now I replace this x by x plus tv. So x plus tv minus what? F. What's f? X unchanged. So I have this. So x minus x gone. So t, this is ti, nothing. So v. And then by definition, Jacobian times v is my directional derivative. Anything multiplied by v is the Jacobian. So it's identity. So therefore, dxx is I for vector case. Okay. If we interpret this as vector field for the PDF thing, then this is what? This is the this kind of figure, right? So it's expanding outward. Okay, I don't want to talk, but you know what I mean. Right? This will be the vector field. What about this one? Now I have AX. So what? Rn to Rm. So first of all, Rn to Rm is linear. Okay, I forgot. Linear. Okay. Because it's linear, then by linear algebra, any linear function from Rn to Rm exists at a matrix such that this is true, right? This is by linear algebra, okay? Then, now I'm saying, okay, now I have Ax, find this. This is now what? This is input is a vector, output is also a vector, and the dimension is different. So, I want fx plus tv. So, what's my f? It's just a. So, all the thing here, I change to this bracket. So, I make this bracket bigger. Done. And then what's the next step? Well, just simple stuff. I put the a to the toolbox. Then now I need this. What is this? F x plus delta minus fx. This is basically calculus, right? Then I just have this expression. Then I have this. What's this? The directional derivative. I have this thing, and this thing equal to something times v. So this thing divided by t take limit is av. So a is the Jacobian. That's what I'm saying. If I have this, then it is a Jacobian times v, right? Then what is this thing? This thing is a tv divided by t. So it's av. So av is jv. Then j is a. So therefore, if you have ax, what's the gradient? A. Okay, and now you should see some funny thing. Why I thought about all these things? Because they are related. What is this thing? This thing, you can see it as norm function composite with ax composite with minus b. So this part is a function. This one is my f. And let's say minus b is a g. And this whole thing is h. So this thing is actually, I'm finding the gradient of f. Yeah, you know what I mean, right? Then this is chain rule. So now I'm doing this thing multiple times, but using stupid way gradient. No, I didn't do the stupid way. The stupid way is this one. Okay, I'm doing the directional derivative, linear algebra, and then now I'm going to do the chain rule. But first I do the Jacobian way. So now you know this, right? So now let's go to another one. Why we learn Gator Frechet? Because if you write something like this, then this J is the Jacobian. Okay. So what is this? This is saying that I have f, Rn to Rm. I want to find gradient y. I want to get this thing. What is this thing? This is saying that f of y equal f of x plus j y minus x plus something else. Now I'm telling you something in the future. Okay? If this f is convex, I don't care. And I have this. So let's go back to here. So what is this part? This part is something that fulfill this. That means this thing decay faster than 1 over t. In other words, this thing have something power 2 or above. Yeah. Which is what? Second order Lagrange remainder. Yeah, then we have this. So now let's say I want to do this. What is this? Given this. Where the heck is this come from? In multi-objective optimization, we are usually given this. So it's like I have m thing, I want to minimize at the same time. So it's like this. Okay, you know, optimization for machine learning, you usually want to minimize this, right? What about minimize this? You don't add them up, you split them, and you want to find the exercise that these two are as small as possible. But here's the thing, this is a vector. For example, what? Larger? Smaller? We don't know. The idea is because in this complex number, right, you cannot say 3 plus 4i is larger than 5, right? We don't know. So we have to turn it into a number. So for multi-objective, we do this. This is f, its output is a vector, then we just take norm of the vector, then it's a number. Then we now can have optimization. So now I want to find this. What is this? Norm composite with a linear vector. Okay. How to find gradient? You can always do this. Don't. I have mentioned this so many times. So let's do the better way. So now I write, okay, I don't write the TV, I just write delta, okay? Then you start with this, okay? And you write this, right? It's simple. And then what? I have assumed f is differentiable. That means I have Taylor expansion. So this one is Taylor expansion. Then this is inner product. I just make it a very big bracket of these two things. Now this few line, I skip a lot of things, but let me tell you what's happening here. This line is basically a plus b plus c and then x, y, z. So I will have what? I will have ax, ay, az, bx, by, bz, cx, cy, cz, right? Then what I'm doing is, for anything that I see delta square, I don't care. So for example, this part have a delta here, this part have delta here. So I will have a delta and then delta x, right? Later, when I take limit, this will die, so I don't write it down. So this is the idea. So what I'm doing, f, this whole thing, and then this part is here. I just split them. And then what? And then this part, f this. I don't write f with delta because take limit, it will gone. So I have this part. And then what about this thing? This thing, I have the smallest thing multiplied with together. I just group it here. Okay, I forgot. I'm not saying I don't write it down. So f multiply this thing, I just treat it as this guy. Because this guy means anything stick with this guy. So f times this thing is here. Okay. And then what about this part? Well, I have this thing times this thing is here. Okay. This j thing times this thing is also here. This f and j times this thing is also here. So I don't write anything related to this one to here. And these are the remaining thing. Okay, so I have this remaining thing. And then what? Now I have this remaining thing. What is this thing? This thing have a delta. This thing have a delta. When I multiply them, they are delta squared. So it's also here. So I put it here. So this part remaining is just j and f. So this part is all the thing with the power 2. And all the thing here is power 1. What is this? This is the same thing, right? I just swap them. Then right? So this part, I have this. What I'm doing? This thing and this thing are same, right? So I have 2 of this. The 2 and the half cancel each other, so there's no power. And then what? So after I combine this, I will have what? J delta f, right? Or I write it as f j delta, right? Now, again, I don't want to see this guy here. I want this guy to stand alone, so I move this to other part. So j transpose here. The same idea. So now I have this. This is what I have, right? The delta here is y minus x. Then the thing stick to it is j. So this thing is gradient. So therefore, gradient of this thing is this j transpose f. What is j? J is also the gradient of multi-value f. So therefore, this is how we get. So the gradient of a multi-output f taking a norm is the gradient, that means the Jacobian transpose with f. And I will only write transpose in this situation. Otherwise, I always write inner product like this. Okay. Now with this in mind, you see this. What is this? Ax minus b. We have this. We have this in the before. This box gives us this. So that means if I view the thing inside, let's ignore the b. Let's ignore the b. If I view the thing inside, ax is fx. Then this transposed part is exactly this a thing. What is this thing inside? It's the f. Ignore the b for a moment. Okay. Actually, b you can keep it because it's translation. So therefore, this thing is also can be used to find this thing. So we consider the thing inside the norm as a matrix transformation on a vector, and we take the gradient. That will be something like this. Then it's the same. This is the third way to do this. Okay. And now this naturally gives us the chain rule. Okay, this is the very abstract version. We don't care. So we care about the useful version. That is, now I have Rn to Rm and R3 vector space. And X is Mn Rm to R and F is Rn to Rm. Okay, be careful of this is Rm thing. So now I have to find this. Okay, so what? I have a function f, first apply on x by f, and then I take this output, put to h, and want to find the gradient of this whole thing. When will this whole thing exist? Well, first of all, of course, the thing inside is differentiable, and then the outside is differentiable, so basically it's these two things, okay? And then what? Then the gradient will be something like this. And this is exactly what I have here. So this is the generalization version. Okay, then what? This is the chain rule, then what about other rule? These are the product rule, sum rule. Just classical trivial. And now we will have what? We'll talk about this. This is a paper. I just did something like this. So I have a f like this, then gradient looks like blah blah blah. Oh my gosh, how do I do that? So let me tell you how I do it. Okay, no detail. This is not important. Okay, so I have what? I have a funny function. H divided by g composite f. where g is just x squared, and then f is f, okay? F is the crazy function. First thing you may ask, why am I doing this? Why am I doing this? The reason is because I know this. So here's the idea. What I want, I have a f, which is some complicated thing, okay? So which is ax b c, I think it is like this, and then dx plus e, and there's no power, this is power 1. Okay, this is my f. My goal is to find this. Okay, so what I'm doing is that I'm doing you can say it's a clever way. So I consider h have a f square. So when I do what? Chain rule, product rule, I have 2 here because this is a chain rule, product rule. This comes from dx squared. But I also have this. So that means what? Now I have this expression, and I know that this is f is a scalar, so I can move this to the other part, so I can have this as what? So this is how I do it. So I specifically think of this funny thing. Then I have this, now I create this equality. What is this 2? 2 is just a number. What is this f? This is just a function f. These are scalar, I can move the other side, and I want to find this gradient. Then if I can find this guy, I find the gradient. Then it will be, how do I find the gradient? So this is, again, the chain rule. So now I want to find the gradient. What is this thing? This thing, h is this, right? So h expression is this big bracket thing square. Why I have a power 2? Now I know why I have a power 2. Because my original function here is power 1. I just make a square such that now it becomes power 2, nice to differentiate. So this is why there's a 2. Now I remember. So basically now I want to do this. Okay, what's next? Now I do chain rule, right? Chain rule, but first I have this. What is this? This part, this one equal to this thing. So I move this whole thing up to here, is what I mean here. So that's why you see, this dx plus 2 plus e is in denominator, here is on top. This ax bc is on top, now it's in bottom. Okay? So now I have this big thing. And then what? I just need to fix this crazy thing. This crazy thing, if you don't use chain rule, product rule, sum rule, whatever rule, and you try to do it by the element derivation, you will die. Okay? So I'm doing this. This guy non-zero, I can use this. This is just the same as what? As the classical calculus you learn. So this is red, and then this is yellow, So red, yellow, so red, yellow, yellow, red, and then the thing is red power, okay, red, okay. This is power 2, so after you do another power 2, you have power 4, okay. What about this part? This part is just this part, originally there, we don't care. Now I have this thing. So then what? What about this remaining step? You just simplify this stuff, there's nothing changed. This power 4 and this power 1, I cancel with get me a power 3. And this thing just go here, okay? And then what? Now, I also have this half term, I combine them. So this part is here, this part is here. So no change. Subtraction. I didn't do anything. I just simplify this into a denominator. So now I'm here. Okay? What's next? Then I do the gradient. Well, how do I do this gradient? Chain rule, product rule. You already know that, right? Then I'm just doing the same thing, but now I have the chain rule. So 2 come out, and then this term, and then differentiate the thing inside. So this is the thing. So let me do it step by step. So let's look at, I do it step by step so that everybody understands what I'm doing, okay? So what I'm going to do is, I write it as g of something, right? So it will be what? d something, and then, right? So this is chain rule, right? Then what is this thing? It's just square. Then of course, this thing is 2, this, right? This is what I do. So that's why I have a 2, the square here. So this black thing is this part. Then I just need to care about this part, okay? This part with a flag, okay? So this part with a flag is what? This part with a flag is just gradient of this, okay? That means I need to find this. Then how do I find this? So first of all, right? This part have no x. When I do this, 0. So I don't care. Right? This is 0, I don't care. What is this? I can always do this, right? What is this? This is the c we see previously. Then, done. That's it. Right? We have a cx, right? We don't care what exactly it looks like, as long as there's no x, this is whatever thing, then we copy whatever thing, right? So that's the idea. So that's why A transpose C, done. Okay, what about this term? Now let's talk about this term. So this term is inner product dx plus e 2 norm. Well, we already know this, right? Ax minus b is what? A transpose Ax minus b. Then there's no half here, so I put a half here. Put back a 2. This plus, then I change the minus to plus and rename b as e and d as a. Done. Yeah. And then now I have lots of things. I simplify again, then I get this. So that's it. So that's how you systematically find the gradient of what? Find the gradient of ax plus bc dx plus e1. And because this is a 1, that's why I specifically make it 2 and then do the square chain rule, because I want to make this 2. Yeah. So this is the idea. Okay, now go back to here. This is how you do this. Okay. Now let's go to the matrix one. It's the same thing. So, okay, I will skip the detail. The idea is this also holds for matrix. So therefore, if you have a matrix function, you also have a vector space. Matrix is also a vector in a sense of vector space. Just now, in this vector space, the vector here are matrix. So in this vector space, Eij is a basis. So that's why all the thing carry over, you have this. So the matrix version, what's the gradient of a matrix function? You just take partial derivative on all the ij, and you collect all of them, then this is the gradient. And you also have what? The 4 things, the partial derivative, the directional derivative, the Cartol derivative, the Fletcher derivative, all the same. So now let's look at the first example. What is this? So the gradient of f for Benet's norm 2, first by linear algebra. Inner product in matrix is trace, and for Benet's norm is defined by trace. So this thing is also the trace of H transpose X. Actually, this is quadratic in matrix. So that's why now you see this. And because this, for Benet's norm, what's for Benet's norm? Okay, for Benet's norm of J is what? Jij, all of them, right? Then if I put a square, then there's no square root. Then this is separable. Because this is separable, that's why I do the elementarize. So, because this is all the ij square, there's no square root because I have a square. So I have this. Then df dx is just this thing, d dx. Okay, and then the 2 go out, and I put the differentiate inside, so I have this. This is just dx squared, right? Dx squared is just 2x. The 2 and the 2 cancel out, so I have xij. So that means differentiation with respect to the ij element is the ij element. Then what about differentiation of the whole matrix is the whole matrix. So therefore, this is true. Now let's do the Fletcher version. So I want to find this, I have delta, the TV. I just consider TV again. So what is the norm? Well, this is norm, right? But just matrix version, it's just trace. So now I do the same again, AB, then I have 4 terms. This is higher order term, so I put it here. This is the first guy, which is by definition is just F norm. What about these 2? They are just the same thing. I flip them, right? So I have 2. This is the gradient, which is correct, right? I mean the X is the gradient. Then, okay. Then what's next? What about ax minus b? Same thing. Okay, I leave it as exercise.